Hey guys, my name's Zach, and my senior projects are black holes. So, over the past centuries, astronomy and physics have led to many amazing discoveries about our universe. Scientists have also used these to stumble upon many fascinating beings throughout space, one being such as black holes. But what exactly are these strange cosmic inconsistencies? Well, according to NASA, a black hole is a point in space where gravity pulls so much that not even light can escape. So, in a sense, a black hole is a point in space where a huge amount of mass has been compressed into a tiny area. So, this infinitely dense space leads to a gravitational pull in which the escape velocity is greater than the speed of light. So, your escape velocity is basically the minimum speed needed for an object to break free from the gravitational attraction of a massive body. So whenever you have mass, you have gravitational pull. The escape velocity is the velocity needed to escape from the gravitational pull. The Earth's escape velocity is 25,020 miles per hour, and the escape velocity of a black hole is faster than the speed of light. So, in a sense, a black hole is pulling at everything, including light waves. So the speed of light is 670,616,629 miles per hour. It's about 186,000 miles a second. Now, according to Einstein's theory of relativity in 1915, it shows that light is the universal speed limit. So nothing can travel faster than the speed of light. So that's where we get this: nothing can escape from a black hole. Nothing can escape its gravitational pull because it's even pulling in light, which is the fastest thing in our universe. So black holes were first theorized by John Michell in 1783, and he wrote a book called Dark Stars, where he suggests this theoretical idea about black stars are stars that have a gravitational pull that's so strong that it even is pulling in light. So it's just a theory at this point. And even used some of the contemporary ideas about gravity to calculate that the mass of a dark star, or a black hole as we call it, the size of the sun, would be a few miles in diameter, which actually matches modern calculations for a black hole of that mass. Next was Albert Einstein in 1915 with his theory of relativity, and pretty much he set the standard for astrophysics, and this opened so many doors for the study in these areas. But his general theory of relativity provides the theoretical basis for a black hole. He shows how the more massive an object, the greater it warps space, so the greater its gravity, and he kind of not discovered gravity, but kind of implemented the physics behind it. So next was Karl Schwarzschild, right around the same time as Albert Einstein. So in 1916, he sent a letter to Einstein with a solution to these equations for that of a spinning sphere, not like a star. So Schwarzschild theorized that if an object's mass was squeezed into a single point, its gravitational field would warp, or cause gravity, the space around it so tightly that nothing could escape. So again, this theory of what if it pulled in everything like light. So most people say that he created this modern concept of a black hole. He also showed the distance from the center of the mass, in which the escape velocity would exceed the speed of light, varies depending on the mass. And I'll go back to that later, because that's something that really has helped us in modern times, known as the Schwarzschild radius. And next, jump to the 60s. In 1967, we have John A. Wheeler. He's an American theoretical physicist, and he really brought this idea of collapsed stars, as what they had become known as, to the forefront. So previously, these ideas, or theoretical talking points, is pretty much what they were, had gone by names like dark stars, or collapsed stars, or Schwarzschild singularities. And that's just what people call them. It was kind of a theoretical idea, but it wasn't really interesting to people. It didn't really interest people. So in 1967, John A. Wheeler coined the term black holes, just said it, and it stuck. And that really got people interested in this. So in a weird way, like coining a term for them, making it sound interesting, actually jump-started the study of these. And so very quickly he became like one of the leading experts on the topic. And really because all he did was coin the term, and it just got all these different people involved. So next, 1971, and this is the first scientific discovery for concrete evidence for black holes. Now, up to this point, it's all been theoretical and math. But in 1971, scientists merged X-ray, radio, and optical observations from telescopes both in space and on the ground, and were able to identify a possible stellar mass black hole known as Cygnus X-1. And this is groundbreaking, because it was the first physical evidence they have of black holes. Now, on to the properties and structure. First of all, the event horizon of the black hole. You may be familiar with that term. An event horizon is basically the outer edge, or the shell of the black hole. You can think about theoretically as a shell. It's not a physical shell, but it's more like it's there, but it's not, like the equator, for example. It's just the part of the black hole's anatomy. So at the event horizon, that's when the escape velocity is equal to the speed of light. Now, once you pass that event horizon is once the gravitational pull becomes stronger than the speed of light. So once you enter that event horizon, you can think of it pretty much as the point of no return for a black hole. So next is the Schwarzschild radius. This was discovered by Carl Schwarzschild in 1916. This basically has to do with how dense something has to become for it to become a black hole. So say, for example, anything can become a black hole. You can become a black hole. This podium, the Earth could become a black hole theoretically if its mass was compressed into a small enough area. So anything with mass like gravitational pull, we already discussed that. Now, the size for something to become a black hole, for a certain mass to become a black hole, can be used by this equation here, which was Schwarzschild's equation. And so you can use that. You have g, which is the gravitational constant, n, which is the mass of an object, and c being the speed of light. And you can plug in all those variables to actually solve for the size of something would have to be for it to become a black hole. Now the singularity, and this is where things start to get really weird. Singularity is the very center of a black hole. At this point, density and gravity become infinite, and space-time curves infinitely. And at this point in space and time, the laws of physics that we have now don't work. They break down, and we don't know why. It's just this, it's all up to theory at this point, because there's no way we can physically or, mathematically understand it. We just have to kind of accept it as it is. It's very controversial up to this date. So, just like anything else, black holes have a starting and an end point. So black holes are formed from the death of massive stars. When stars run out of fuel to sustain themselves, they collapse in on themselves, blowing out material in a massive supernova explosion. When a star collapses in on itself, its mass is compressed into an infinitely small space, thus leaving behind a black hole. Now, do note that not all stars will become black holes. Only stars with very large masses can become black holes. Black holes can actually grow throughout their life. They can grow by taking in the masses from nearby material that adds to the black hole's mass. And some extremely massive black holes even have the ability to swallow other stars completely. Now you think about, black holes swallowing stars. What about black holes swallowing black holes? Black holes actually can merge together to form. If two black holes were to merge, they could become one giant black hole. Now this merger would be something that's huge, and it's a huge catastrophic event that produced a tremendous amount of energy, and it actually sent ripples throughout the fabric of space-time. The tremendous energy released from the black hole merger, and these waves that would be sent throughout the fabric of the universe, basically called what scientists call gravitational waves. Now, gravitational waves, like I said, are massive ripples to the fabric of the universe, and they're actually predicted in Einstein's theory of general relativity. However, no evidence was ever found for them. It was all just theory until September 14th of 2015, which was just last year. Scientists actually observed these gravitational waves impacting our Earth. Now, they first observed it in September 14th of 2015. However, they announced that they discovered that this is actually what they were. They actually were gravitational waves, February 11th of 2016. So this was just a few months ago. This is groundbreaking stuff that's happening. Scientists announced in February that they had recorded the sound of two black holes colliding over 1 billion light years away. So you can see here, this is how those waves, it's actually the fabric of the universe that would be just like ripples in water. So next, black holes actually do have an end to their life. Originally, it was theorized that they lived forever. However, in 1974, British physicist Stephen Hawking announced that black holes are not black, but actually glow with heat and radiate. So it didn't really make sense. If nothing can escape a black hole, how is it going to radiate something? How is energy going to come off? And that was the question for a while. And Hawking soon came back with an answer that the heat radiated by a black hole is paid for not by energy flowing out, but by negative energy flowing in. That's a weird thing to think about. It doesn't really make sense. It's the process that he theorized known as Hawking radiation. But to understand it, you have to understand quantum mechanics and understand a thing called quantum field theory. So when you look at quantum field theory, you got to look at empty space on a subatomic level. So when you get to quantum mechanics, empty space is not really empty, but it's filled with tiny pairs of subatomic particles. In an instance, these particles, a pair of particles, will appear and then one of them will have negative mass, one has positive mass. This is happening everywhere in throughout observable empty space. And so these particles, they come into existence and they destroy one another instantaneously. And these particles, they have no measurable mass and no gravitational pull, but we can, through quantum mechanics, we can tell that these exist. And so when this happens on the edge of a black hole, basically what you get is the one with the positive mass, it will go off, actually escape from the black hole to be observed as a physical particle. However, while the one with negative mass gets pulled in to the black hole, actually decreasing the mass. And so as you move on to Hawking radiation, the particle that actually can escape, if you will, so you look at the event horizon. If you have on either side of the event horizon, one gets pulled in and one is just strong enough to get away. So the one that can get away is observed as radiation, and the one that gets pulled in actually takes away from the mass of the black hole. It's a really odd concept, but it's still, that's the process in which black holes decay. And it's an extremely slow process. However, as time goes on, it does speed up. But the amount of time it takes is millions and millions of years. And so by the time the last black hole that ever was decayed, no one would be around to observe it. So a lot of times we see stuff about black holes in astronomy and physics in science fiction movies, and oftentimes a lot of it is not actually true. It's not accurate. So one of these common misconceptions that science fiction leads us to believe is that black holes are these giant cosmic vacuum cleaners that take in everything around it. And that's not actually true. Although black holes do have a strong gravitational pull, they don't have a strong gravitational pull for long distances. Now they can pull once you pass that event horizon or very close. It is a very strong pull, but it doesn't pull for long distances. The best analogy to look at this is black holes are almost like giant cosmic Venus flytraps. So whenever something comes in a certain area, then it would take it in. Another one is that we can actually see black holes, and this is kind of an odd subject to look at because it has to do with gravitational lensing. Now, when you observe something, you see it, and light reflects off of that object and comes back to your eyes, so you observe it. Now, in a black hole, light goes in, but it doesn't come back out. So we can't directly observe it, but we can indirectly observe them through this this strange phenomenon known as gravitational lensing. So basically, when you get something like this, strong gravity can actually warp light. And so as this GIF here is from a galaxy, this is someone created this isn't actual footage, but it's a galaxy that's behind a black hole. Now the galaxy is not in danger of the black hole, but the light coming off is. So as the light is reaching our eyes, the gravity around the black hole actually warps the light, but nothing comes through it because the gravitational pull of the black hole is sucking in all the light. So you can see the light warp around the black hole, but nothing actually coming through it. So in a way we can indirectly observe them, but not directly observe them. And another one is that black holes can lead to other places. So, say you go into a black hole and a certain movie will say you come out somewhere else, another place in the universe or another place in space or time or whatever. And it's actually, there is solid evidence backing this up. It's plausible by something called wormholes. Now, wormholes are basically a theoretical passage through space-time that create shortcuts across long journeys to the universe. And wormholes are another prediction of Einstein's theory, but there's no evidence to back them up yet, so it's all just theory at this point. So mathematically, wormholes are possible, and they don't work in any way that violates the laws of science, but they actually take advantage of the dimensions of the universe. So say if you're traveling from 2 points, you want to travel from here to here, you would travel the distance in between. However, a wormhole would do something like this. If I can get to focus, like that. So you have 2 points, but if you do that, the points are right next to each other. Originally, they're a long way away, but a wormhole would do something like bring the 2 points instantly close to each other, so you could travel from one to the other instantly, even though it is a distance in between. So mathematically, they are possible, but there's no physical evidence backing them up. So finally, what would happen if you were to go inside one of these black holes? Now, it's really weird because from you going in and someone observing you, you would see totally, completely different things. So first of all, time is completely different inside of a black hole. So when you get a strong gravitational field, it's theorized that time actually acts different. So as you approach this massive body of a black hole, time would actually start to slow down because of the gravity. And you would actually experience time slower than someone observing you. So if you and your observer had a clock, and you went to the black hole and went inside and were somehow able to get back out and compared your clocks, theirs would actually be ahead of yours because they're experiencing time at a faster rate than you are. Now, falling into a black hole, this is where it's interesting stuff. So again, your experience would be different as you approach from someone else. So as you approach the black hole, you become closer and closer and closer to this just dark abyss. Now, eventually, your observer would see you freeze in space, and they would see you freeze at the point of the event horizon, because once you pass that event horizon, there's no light coming back out to get to their eyes. So the last point that they were able to observe you would be the event horizon. So to your observer, you would fall and fall, and you would eventually freeze, and you would just seem frozen in space, your body would, and it would eventually red shift, and then you would just disappear. However, for you, you would continue falling, falling, and falling like it's no big deal. So the closer you get to the singularity, which is the center of the black hole, the stronger the gravitational pull gets. So the stronger the gravitational pull is between two areas. So like on Earth, the gravitational pull is pretty constant throughout because it's not as strong. Now in a black hole, the closer you get to the singularity, which is the point of the utmost gravitational pull, it's actually stronger between two areas. So you get to a point where your feet would actually be, assuming you're falling straight down, your feet would actually be pulling stronger than your head would be by the gravitational pull. So this leads to a process which is known as spaghettification. You can't make this up. This is actually a scientific term. So spaghettification is the vertical stretching and horizontal compression of objects into long, thin shapes in a very strong, non-homogeneous gravitational field being caused by external tidal forces. So essentially, you can look at it like Laffy Taffy. Your body would be being stretched infinitely, long and crushed at the same time. The very molecules that make up your body are being ripped apart at this point, and it's all by gravity. It's pretty crazy stuff. So once, at this point you're pretty much dead, but your molecules are still falling, right? So what happens next? It's up to debate. No one really knows what happened because, like you said, the laws of physics we have break down. They don't work. And so, some assume that, maybe there is a wormhole to one, maybe the molecules that make your body would appear somewhere else, or maybe they would just disappear and violating all the laws of physics, but you're doing that anyway. So it's really, just up to debate. So no one theory has any physical evidence to back anything up, but scientists, quite frankly, have no clue what would happen. Black holes are these strange cosmic entities continue to fascinate scientists and push the boundaries of our imagination. Black holes are a true testament to the beautiful craftsmanship and exquisite intricacy of the hand of God. Any questions?
So when the scientists observe the waves of gravity, what they see, did the sun get brighter?
What do you mean?
When the plus falls in the gravity.
Oh, with the gravity, basically, so you have the best way to imagine is waves with water. So when you have waves in the water, they kind of collapse once they reach something. Well, once those waves to our universe that actually impacted the Earth, it actually caused a shift in the Earth. Like, it was detectable. It was like vibrations, sort of, kind of. And so once those waves, they impacted our Earth, Mr. Taylor was telling me it actually decreased the mass. Like, it pushed the Earth together by some barely measurable factor, but it was still mathematically they were able to see it. And so these instruments they have that are extremely sensitive, they are able to detect that vibration or that wave as it came through and actually impacted our Earth.
Did the Earth go back?
Yeah, I would assume so. It's when you get to stuff like this, it's way above my head. I'm just trying to put it in its simplest form. But do you have a question?
Have scientists actually tried to send stuff into black holes?
The nearest black hole we have is millions and millions of light years away. So this stuff is all math and theoretical. That's why theoretical physics is such a huge thing, because there's no way we could able to, in any of our lifetimes, reach any of this. But still to try to figure it out and see how it works is still an interesting topic. So, other questions? Terry?
What are the odds that anything could become a black hole? Like, what are the numbers on that?
Well, you look at, so we'll take the Earth, for example. If you crush the Earth using Schwarzschild's equation, you plug in the mass of the Earth with the gravitational constant, the Earth would actually be about the size of a peanut. If you crush the entire mass of the Earth, the entire mass, maintaining its same mass, down to the size of a peanut, the Earth would become a black hole. So you would still have to maintain the exact mass of the Earth while being in a space no larger than a peanut. At that point, the gravitational pull, the mass would be so dense, the gravitational pull would be so strong that you would have a black hole. And so at this point, there's no really giant cosmic crushing device we have to make black holes, but that'd be kind of an interesting thing to work on.
English translation of that.